The 266 primary system consists of phase 1, phase 2, and phase 3 layered, and all three of these layers are brought together. They're powered from a three-phase alternator. On either side of the top and bottom of the 266 primary system, we have induction coils, 2.4 Henry induction coils. These have about 7,000 ohms reactance at our frequency from the alternator at 465 hertz. This means that for every milliamp of amperage circulation in the secondary, there will be 7 volts across it. We're going to measure the voltage anyway. Now, this is a bold claim. I don't know if Eric Krieg has got his money out yet. But this system is powered from an over-unity state. And we're going to demonstrate that right away. The way we're going to demonstrate that is we're going to look at our power in and our power out. I said it's powered from an over-unity state. That does not imply that when in operation it's over-unity. But we'll look at all these aspects by 3 different readings. The 3 different readings that we'll take will be the function of the machine, with no secondary loads, the function of the machine with just the coil load, and the function of the machine when that coil load is given a resonance. Here on this diagram we can see we got an amperage meter in place on that circulation. As long as the arc gap isn't firing and it's open circuit, that amperage meter will measure the amount of amperage circulation in the secondaries. Thus we can compare the amperage circulation in the secondaries to the primary amperage circulation and form voltage ratios, etc. on down the line. And going back into the past research, I wanted to find out what the turns ratios were, and there were 67-to-1 turns ratio between these 140 ohm secondaries and the pancake coils, which are, which are 0.5 ohms, consisting of 2 bifilar wired mega cable speaker wire spools. Now what we'll do is we'll go in there and turn our device on, and in time constraints try to illustrate what these ratios are and why we can claim that the machine operates from a state of over-unity. We'll go in there and put up our barrier and turn the alternator on, get a quick picture of the alternator, where everything's powered from. Some darkness right there, probably can't see too well. And then there's the motor, and I don't think the alternator can be seen very well. But that's the alternator that produces the 3-phase for our experiments, and these will probably be done with an unenergized field. So let's get in there and get to work now. We'll focus on our turn-on state. Excuse me. There's our turn-on state to be noted. 3 red meters in the background are the stator line amperages, and phase 1, 2, and 3 phase amperages, and the smaller yellow meters are the voltages on each phase. Obstacle course. Okay, right now then, we're going to show our 3 stator lines are pretty equal. phase amperage is what we're really crucially concerned with. And down here we have our secondary amperages. And then in front we have our arc gaps. We'll go ahead and measure our arc gaps real quick with the voltage meter. See if that voltage meter's in there. Where is it? There he is. On the top, secondary, we have 37 milliamp circulation, showing 237 to 240 volts. On the bottom secondary, we have almost 20 milliamp circulation, showing 115 volts. On our primaries, the top layer, you can't see that voltage meter very well for phase 3 to the right. We have 1.1 volts enabling 0.185 amps on the top layer, or 180 milliamps at 1.1 volt. It produces 37 milliamps. 181 divided into 37. 37 milliamps. 181 milliamps divided by 0.0. I'm losing my mind here. 182 divided by 37. Okay, we got 5 times less, 4 times less amperage in the secondary. We should have done a 4.9-fold increase in voltage. However, as we've already shown, that would be 1.1 times 4.9 or 6 volts. Instead, we have the phenomenal amount of 220 volts across that arc gap. .237 volts. So we can see that the 67:1 turns ratio, we should only expect 67 volts, but we got triple that or more. On the bottom side, we don't have as high of a voltage. We only had a household voltage on that side. But yet, on its input, we can see that its input is only 150 milliamps, downgraded to 20. Well, that would be a reduction of 15 divided by 2, or about 7.5. So we should expect its 1.1 volts multiplied by 7.5 would be 8 volts or so. And yet, on that side, we are obtaining, again, some 115 volts. So that side we got 133 volts. So there you see the phenomenal efficiencies of this air core transformer. And I think that we'll call it quits for this video to show that, and we'll return with measurements of the 3 states.